So at this point, we were just exploiting spherical symmetry and our freedom to do general coordinate transformations. Now we start the actual job, which is to find out what kind of A and B would make this metric Ricci flat. Okay, so we're solving for Ricci flatness. And before we solve, of course, we need some boundary conditions. And the physical boundary condition is that far from the source, the gravitational field vanishes. Okay, gravitational field vanishes. That means the metric should become Minkowski space. If there is a spherical mass distribution very far from the source, you will not feel the effects of the because gravitational field will fall down with distance, and at infinity or spatial infinity, you should expect the metric to become Minkowski. So that means G00, which contains the information about little a, should become -1 as r goes to infinity. So spatial direction r, the spatial direction goes to infinity, and GRR when r goes to infinity should approach 1 plus 1. So this in turn, if we look at the exponential parameterization, if this goes to 1, that means A must go to 0 and B must go to 0. So A and B must both approach 0 when r goes to infinity for all times, regardless of the time. It doesn't matter because this metric must become Minkowski very far. So then for all times at r equals infinity, A and B must approach 0. Okay, they must vanish. All right. Next thing is to solve for this Ricci flatness. For that, we need to, of course, work out the connection coefficients, Levi-Civita connection coefficients. And then from the Levi-Civita, we need to construct the Ricci tensor coefficients. Okay, so this is worked out in the notes. I will not, I will spare you the calculation, but this is very straightforward. It's just calculus, you just differentiate. That's all. Now, in actual research, we don't do this by hand. Routinely, these are done in the computer using some symbolic manipulation software like Mathematica or SageMath. Mathematica is a proprietary software, so you have to purchase a license to use it. But SageMath is an open source. I almost entirely work on Mathematica because our institution has a license for that. And I've never exposed SageMath, but I know this is an open source alternative which a lot of people use. But this calculation of Levi-Civita and Riemann and Ricci, this is usually done on a computer because there are many coefficients and people make errors while calculating these by hand. And professionally, it is not done. Professionally, they are done on a computer. Okay, the code is all there. Maybe I will share in the next class, next lecture, that Mathematica code. Okay. Anyway, we can compute this given the metric, very simple metric which I have given you. From this, you can compute the Levi-Civita connection coefficient, and you can also compute the Ricci tensors for using these formula. Then we need to set those coefficients of Ricci tensor to 0. So, for example, I can look at the TR component of the Ricci tensor. If you plug in the metric which I showed you, the ansatz, then turns out the TR component is B dot by R, where B dot, remember the dot is derivative with respect to time, with respect to t, partial derivative with respect to t, and I'm going to use prime to represent the derivative with respect to r. Okay, so dot and prime respectively represent the partial derivative with respect to time and the partial derivative with respect to r. Okay, we clean this up. All right, so the TR component of the Ricci tensor works out to be B dot over R. So demanding that this vanish tells you that the partial derivative of B with respect to time must vanish because R is not 0 always. That means B is purely a function of R. Okay, B has no time dependence. Remember, B is the coefficient metric coefficient in the GRR term. So that must be completely independent of time. Okay. Then we can look at this particular RR plus e to the b minus a RTT. And this combination is natural because when you write down the two forms, you will see that they differ by e to the b minus a. That kind of a combination. Terms are very, it's easy to group them if you multiply it by this factor of e to the b minus a. Okay, yeah, this grouping becomes very easy. I'm not going to write the detailed formula because they are kind of long and not very intuitive or insightful. So instead, if you look at this combination, because R Ricci tensor component vanish, this is equal to 0, of course, because both R sub RR and R sub TT vanish. And so this, on the other hand, you can work out from the metric which we have written. And this turns out this demanding equal to 0 tells you that the sum of the partial derivative of A with respect to R and B with respect to R must vanish. And since B is independent of T completely, which we just proved, that this condition implies that A must be a sum of two functions. One is, of course, minus B, the same coefficient, which is the function of R, purely a function of R, and the other constant of integration, which is purely a function of T. Because when we do integration with respect to R, we have an undetermined function of pure function of T. Okay, so these two conditions immediately tell you that A, B is independent of R, T, I'm sorry, and A is given in terms of B, or A differs from minus B by an undetermined function of time. Okay, let's move on. So next we can look at the R theta theta condition, or theta theta component. In this case, this component looks something like this, and demanding it vanish, and the fact that A prime is minus B prime, we can solve for e to the b completely. And turns out exponential of B is given by this. This ODE can be solved very easily for B. And it turns out exponential of B is given by this 1 plus C over R, whole thing raised to the minus 1. Okay? And C is the constant of integration. Remember, this is the first order ordinary differential equation, so solving it will leave us with an undetermined constant of integration, which I'm calling C. Okay? So we have determined e to the b already, and now it's A. Now let's remember that we have the boundary condition that far from the source the metric should become Minkowski. That means A and B should vanish, and B automatically satisfies this condition, because if I put R equals infinity, then this is 1. Okay, B is 0 or e to the b is 1. So it's very obvious that e to the b is 1. Okay. On the other hand, so b is e to the b is 1 means b is 0. So as R goes to infinity, this tells us that this term will go to 0. But A also has to go to 0 as for all times. That means this f of t must be 0. Okay. Because this is R independent, so taking the limit at R equal to infinity should not matter to this term at all. So if it is 0 at R equals infinity, it is 0 everywhere. So ft must be set to 0. Okay, so ft must be set to 0. Okay. So we applied Ricci spherical symmetry and then Ricci flatness, and that immediately led us to this form of the solution. The coefficients are determined except for an undetermined constant of integration. So this is basically the Schwarzschild solution. So this is kind of amazing because the solution is static. None of the coefficients depend on time. So it's completely time independent. We never asked for time independent. All we were looking is spherical symmetry. Not only time independent, this is time reversal invariant. That is, there is no, if I switch t to minus t because of the square in dt square, the metric doesn't change. So whether the symmetry has time reversal independence. Okay, so t going to minus t, it remains the same. So not only are the coefficients time independent, but they are also immune to the direction of time. Okay, they don't care about it. So this kind of solution, which is time independent and has time reversal invariance, are called static solutions. So it turns out that spherical symmetric solutions are always static. So this is very difficult to grasp intuitively, because one can imagine a situation which is dynamic. For example, consider a sphere, which is a spherical mass. But let's say as it happens in astrophysical situations, for some mechanism, the spherical distribution is blowing up, puffing up, and then contracting to some small size. And it doesn't even have to be periodic, but some randomly it blows up, and after some time it contracts, again contracts a little bit more. So it might be dynamical, but maintaining the spherical symmetry. The size of the sphere might be changing with time in any way, but the solution which we wrote down doesn't change, doesn't see that variation in the size of the matter distribution. Far or out of that, you just see a single time independent gravitational field. So the gravitational field, being time independent as well as time reversal invariant, is very strange, given that the mass distribution could be a sphere which is growing and shrinking at randomly, okay, some dynamical way. So this theorem is very non-trivial, and this goes by the result of Birkhoff's theorem, after the American mathematician, Harvard mathematician, who actually proved this. But this is one of the main results, which tells you in GR, which tells you that spherical symmetry almost is same as static. Okay, if you ensure, if you have a spherical symmetric situation, then the solution will always be static. Okay, time independent and time reversal invariant as well. This is a counterintuitive result, but very strong result, that all spherical invariant solutions of GR must be static solutions. Okay, now the only thing left is to determine this C. In particular, for this we will take help of the Newtonian limit. In the Newtonian limit, most of you know, G00 is eta 00 minus 2 phi over c squared, where phi is the Newtonian gravitational potential. So I'm talking about a case in which the gravitational field produced by this spherical object or spherical distribution of matter energy is weak. In that case, we can look at this Newtonian limit. And in the Newtonian limit, the spherical distribution, also I can take a sphere of mass m. So a spherically massive object of mass m. We already know the potential, which is something like this. Now if I plug this back here, if I plug this back here, immediately leads to the identification of C as minus twice d Newton times mass divided by c squared. Okay, so even this constant C got determined if I take the Newtonian limit and relate it to the mass of the distribution. So it makes sense, of course. The bigger the mass, the stronger is the deformation of the metric from Minkowski. So C is determined. Now we can write down the full solution, which is known as, this is the final form of the solution, in which you have dt squared with some constant over r, dr squared some constant over r. I could have used natural units in which these factors of c squared will not be there, but I've kept it because in the next lecture we are about to discuss the Newtonian approximation, or in the Newtonian regime, or corrections to the Newtonian regime. So that is why I've kept the c squared around. But in most books, the c squared is not there. And then you have a bit simpler looking metric, which is twice g Newton times m over r. Okay, so this is the Schwarzschild solution, the final form. We have succeeded in writing it down. And then we can ask, okay, well, this is entirely outside the sphere. But what if I take a hollow sphere or a spherical shell? Okay, if I take a spherical shell, now inside is also vacuum because there is nothing anymore. I've taken a spherical shell, not a fully solid sphere. So I should be, that is also spherically symmetric metric. So outside is spherically symmetric metric, and we have the Schwarzschild solution. Inside we should also have the same solution being valid, right? A bit more generic form, which is this with the C. And the natural question is, what is the solution inside? And of course, the solution will include the origin, which is r equal to 0, and there is nothing here. So we expect the metric to be regular, that is finite at r equal to 0, finite derivative. But if I look at the general form of the solution, if I take r equal to 0, this metric blows up. So at r equal to 0, this is not regular, unless we set c equals 0. Because then this c equal to 0 set, this term vanishes entirely, drop this term. So for the interior solution, we will take the boundary condition as c equals 1, c equals 0, I'm sorry. So we will set c equal to 0 for the interior. Finiteness of the metric at r equals 0 implies that c has to be set 0 for the inside. So the interior solution I've written, if c is 0, then we just have Minkowski. There's no difference. If c is 0, as you can see, this is just a Minkowski, not in Cartesian coordinate, but in spherical polar coordinate system. So for the spherical shell or hollow sphere, the solution for the outside is the Schwarzschild, which is given, and m is the mass of the shell, and inside the metric is Minkowski. So this is the case for the hollow shell, hollow sphere. Minkowski inside, Schwarzschild outside. Now, this is a generalization of Newton's theorem in Newtonian gravity. Newtonian gravity, most of you have read this theorem. If you have a spherical shell, then from outside, it will appear the gravitational potential is same as that of, as if the whole mass of the shell is concentrated at the center of the shell, that is of point mass, and concentrated at the center of the shell. That is how it looks outside. And inside the shell, the gravitational field vanishes. There is no gravitational field. Okay, so this is precisely that situation. Outside it is Schwarzschild, which is same as that. It doesn't matter whether the shell is hollow or rigid. This is the cell just sees the entire mass, and inside it is Minkowski, so flat. So this is Newton's theorem in general relativity. Okay, we call this Newton's result for the hollow shell Newton's theorem in general relativity because it shows it's Minkowski inside, Schwarzschild outside. Okay, so that will conclude our lecture. A couple of things I will remind you that, as I said, the whole analysis can be generalized for arbitrary dimensions, which you can find in the notes. And most likely I will leave the assignment problem in which you can change the situation a little bit, make it a bit more interesting by including a cosmological constant term, and ask for solutions, vacuum solutions, with the cosmological constant turned on in the left-hand side, in the middle. So instead of looking for spherically symmetric solutions of Einstein equation without the cosmological constant, you can ask, what do vacuum solutions for Einstein field equation look in the presence of a cosmological constant? So in that case, obviously the Ricci flatness will not be there, but there will be something else. So if you take trace, you'll get another condition for the Ricci tensor to obey, and you have to solve that equation in those cases. So maybe I will leave that for homework, which is a generalization of what I did. Instead of r mu nu equal to 0, you solve for r mu nu equal to something else determined by the cosmological constant. And when you solve for those equations, you should see that, first of all, Birkhoff's theorem will still be true, that you still get time independence from spherical symmetry, despite the fact that there is a cosmological constant turned on. And two, there'll be, in this metric, there'll be an extra term, plus, which will be proportional to the lambda. Okay, so there'll be an extra term. So most of the steps will go through, except r mu nu you cannot put equal to 0, but the right hand side will be non-zero, and you have to work a little bit to solve them, but they're pretty straightforward. Okay, with that note, let me end the lecture here and provide a summary and outlook. So we were looking for vacuum solutions of, I'm sorry, this is a typo here, of full nonlinear GR, and they turn out to be Ricci flat geometries. Okay, and spherical symmetry forces the metric to be static. This is Birkhoff's theorem. We first defined what spherical symmetry is in terms of scaling vectors and the SO3 algebra, and we used Frobenius theorem to narrow down the ansatz of the metric and other symmetry of general coordinate transformations. And we showed that the spherical symmetry force these metrics to be static. Then the Ricci flat condition and the Newtonian limit led to the Schwarzschild solution. With some help from the Newtonian limit, we were able to write down the Schwarzschild solution. As I said, that this is the unique solution to the spherically symmetric metric outside sources. And then we discussed at the end the case of the spherical shell or a hollow sphere. And we showed that Newton's theorem, which is usually true for Newtonian gravity, actually goes through unchanged in GR. You have the same thing inside the gravitational field is 0, outside is same as that of a point mass situated at the origin. Okay. In the next lecture or two, we will study the Schwarzschild geometry. We will probe them using geodesics. Okay. And we will highlight the contrast to Newtonian or Keplerian orbits you would expect. In Newtonian gravity, if you have a massive object, then for the gravitational field produced by a point object, spherical or a point object or a spherical object, we know the orbits are Keplerian orbits, and we will see how we get a departure from that in general relativity. And we will also look at the motion of light in gravitational fields, in particular in the Schwarzschild field, and we will discover two effects of motion of light, which is deflection of light, gravitational deflection of light, and gravitational retardation, as if light will appear to slow down. Sometimes some people call this the Shapiro radar delay, etc. Other things. Okay, with that note, I will end here. Thank you very much for your attention, and I will see you.